Okay, so this is some work that I've been doing with Nick Brummel, some of you will know, in Santa Cruz. It's been evolving on a suitably long astronomical timescale. It's kind of almost done, so it seemed like a good chance to say a little bit about it. So it's to do with magnetic layering. So layering, I mean the formation of a stepped structure in one of the variables, okay, in a turbulent system. So it might be density, might be temperature. Typically it's everything, and they're often called staircases for the obvious reason. And layering occurs in all sorts of systems, actually, all sorts of turbulent systems. I'm only going to, whoops, it does that sometimes, it doesn't like to advance, right. I'm only going to be talking about double diffusive layering today. So this, before we get on to anything to do with MHD, this is a double diffusive system. So double diffusion means two components contribute to the density, and the classical case is temperature and salt, and sometimes called Thermo-Haline convection. And this is a picture that I took from a paper by the Santa Cruz group. I think Toby might even be on this, Mirror et al. In 2012, which shows the salt concentration after a certain time in a 3D simulation, forming these layers. Okay, and this is there's two important regimes in double diffusive convection. One is the salt finger regime, and the other, which is what I'm going to be talking about today, is the so-called diffusive regime. So the diffusive regime is a destabilizing temperature and a stabilizing salt gradient. And this is an interesting phenomenon. It's intrinsically interesting because you think you've got a turbulent system. Why doesn't it just make everything more homogeneous rather than forming inhomogeneities? But it's also of interest because the turbulent transport in a layered system, once it comes into a layered state like this, is much greater than in the non-layered state. So if you're interested in doing, let's say building a model of stellar interiors or whatever, where you have to parameterize the turbulent transport, then it really matters. It really matters if it's layered or not. So you need to know this. So the question we asked a long time ago was, could you get something similar in a magnetic system? Can you get double diffusive magnetic instabilities that lead to layering? Because if you can, then for reasons I've just said, that could be important in modeling transport in stellar interiors. So here's a quick run through of the equations of Thermo-Haline convection. I'll get to magnetic fields shortly. Often these are done in an unbounded domain. So in an unbounded domain, then you have to adopt an intrinsic length scale, which is this one, which is typically what makes them, well, it's what makes the Rayleigh number equal 1. That's not so crucial. There's only one, ostensibly, you've got rid of a Rayleigh number, and you just have the ratio of Rayleigh numbers in this problem. So you have three equations. The top one is a vorticity equation, temperature and salt perturbations. The second one is the temperature equation. The third one is the salt equation. And the signs of the gradients, in the way we've done it, they appear here. There are various ways you can do it. So there's a density ratio, R0, which is the ratio of Rayleigh numbers, if you like. There's a Prandtl number and there's a diffusivity ratio. And as I said, I'm going to consider the diffusive regime, which has the gradients in this way. Okay, what if we did magnetic buoyancy? So magnetic buoyancy is an instability driven by a stratified field. Let's consider 2D magnetic buoyancy. So no bending of the field lines. Then we don't have heat and salt. Now we have an entropy gradient and a magnetic gradient, or really a B over rho gradient. Okay, and you could easily, as you can see, you could concoct Rayleigh numbers to go along with these. If you study magnetic buoyancy in what's called the Magneto-Boussinesq approximation, that is a seminar of itself, so you just have to bear with me. Then the equations are these. And we should be thinking, how do they look compared to what we've just seen for thermohaline convection? Well, the vorticity equation is pretty similar. The magnetic pressure equation is like salt, or minus salt, if you like. But this one, the temperature and the magnetic pressure come together here. So this is not in standard double diffusive form as it stands, okay? You can make it in that form through this change of variable, which in advance is not an obvious change of variable. So this change of variable, which involves temperature and magnetic pressure into this new delta T star, and the gradient is a mixture of the adiabatic gradient and the entropy gradient and the B over rho gradient, puts it in the right form. If you think double diffusion is the right form, it's standard form at least. And the Rayleigh numbers map like this, okay? And the main upshot of this, the main interesting upshot of this, is that you might be familiar with the Rayleigh, with the stability diagram for double diffusive convection, which is this one on the left, with a Rayleigh number and a salt Rayleigh number. And this is what it looks like in the magnetic problem. This is not a new result, this is an old result, but it's crucial for what I'm going to say. What you can see is that there is instability in what ostensibly you might think of as the stable quadrant, the bottom right, okay. Now, the question we asked is, can we have layering? That's even more weird, right? Layering in the stable quadrant. We know from like the simulations I showed that you get layering somewhere in this little triangle, well, in this triangle here, below the neutral line, the top heavy line, and above the stability boundary. But we don't know, without doing the calculations, whether we get layering in the stable quadrant. So stable would mean subadiabatic and B over rho decreasing with height. So you can do the simulations. So this is what we do, is we actually do thermohaline simulations and translate into the magnetic problem. So these are at 3 different times, and there's 3 different quantities. So the quantities are the vorticity field, the variation in entropy, and the variation in magnetic pressure. And this is how layers form. They actually form, you know, they swallow up the non-layered region until you have a beautiful layered structure like this. There is some evidence of layering in the vorticity, but it's much less obvious, okay? So this is the 2D version, if you like, of what I showed, the 3D picture in thermohaline convection. So yes, you do get layering in the stable regime. Now that is quite a weird result if you didn't know about thermohaline convection, because this is what the thermohaline convection looks like. These are the same problem. This is the thermohaline convection mapped into the magnetic buoyancy problem. So the thermohaline convection looks as you would expect. You have sharper steps in salt because the salt diffusion is much smaller than the thermal diffusion, and you get a more smeared staircase in temperature. But the temperature one here, remember, is destabilizing. It's hot on the bottom, cold on the top. Salt is stabilizing. Now here's the magnetic problem. Both these gradients are stabilizing, if you like, right? The B over rho to the gamma is increasing with height, and B over rho is increasing with height. And so you can see B over rho looks like minus salt, rho looks like rho. And how you get staircases in what started off as a stable structure is that it has to bend itself backwards to get these amazingly sharp backward facing staircases, actually. So this is looked at as a pure translation from the thermohaline problem. You think, oh, okay, that's how it is. If you didn't know about the thermohaline problem, this is a very surprising result, that you start with 2 stable gradients and you get this layered structure. And as I said earlier, it's important because transport goes up a lot as the layers form. These red lines are the 3 times on that previous plot, or 2 previous, 1, 2 earlier. And you can see that this is turbulent transport of entropy, turbulent transport of magnetic pressure. Okay, and it goes up considerably, and it will keep going up as, I mean, in a simulation, the layers merge actually, and it will keep going up. Okay, what's the upshot of it astrophysically? Well, in a radiative interior, you might well have a well, you will have a sub-adiabatic gradient, but you might also have field increasing with height. And so layering is a distinct possibility, and then transport really matters. It's a tricky problem, mixing in radiative interiors. It's not like convective mixing, where convection is the big player. In radiative interiors, there is all sorts of stuff going on, and it's very hard often to say who is winning. Mainly magnetic field is seen as an inhibitor. We are saying that it could well be a driver of layering instability. So just to give you a flavor of the mess that is mixing in radiative zones, I show you this from one of Jean-Paul Zahn's papers. You don't really need to take it in, except to see it. You can see that there's a whole load of stuff going on, and it's hard to tell. It's hard to pull out a prime candidate. So in some sense, we are muddying the waters. We are saying it's not, that's fine, Toby, thanks. It's even worse than this, because in this picture, magnetic fields typically, you think of something and then you say, oh yeah, but it'll be inhibited by the magnetic field. It's not like that. The magnetic field can drive a whole new mixing process. And there are red giant stars, their observations don't match current mixing explanations. And so this is a candidate for extra mixing in those. Final slide, you might say, ah, yeah, it's quite constrained. You've got your 2D and you've gone for a thermohaline analogy into the Buoyancy, all true. 3D and 2D thermohaline convection might be different. Actually, it's not that different for the diffusive regime, but of course 3D and 2D magnetic instabilities are not that different, because the 3D, the magnetic field imposes a strong anisotropy, and 3D magnetic buoyancy instabilities actually do look quite like 2D magnetic buoyancy instabilities. And it is clearly of interest to push beyond the analogy to see if you can get layering beyond the Buoyancy approximation. Okay, I'll stop there. Thank you.